Hello dear students, welcome to the course of Thermodynamics 1. Today we are going to discuss about mixed cycle, and in particular we are going to discuss about numerical or dual cycle. So given data for dual cycle is here. A compression ignition engine working on the dual cycle takes in 2/3 of the total heat supply at constant volume and 1/3 at constant pressure. Now further, the compression ratio is 15 to 1. The maximum pressure in the cycle is 50 bar. Air intake takes place at 27 degrees Celsius and 1 bar. Determine the temperature at each point of the cycle and thermal efficiency of the cycle. Assume Cp and Cv as given in the data. Here for your reference, the PV and TS diagram of dual cycle is presented. Now let's write down the given data first. So as you can see, the compression ratio is 15. Further, the maximum pressure of the cycle is 50 bar. So if you observe the PV diagram, then P3 and P4 is the maximum pressure, that is 50 bar. So P3 is equal to P4 is equal to 50 bar. If you convert it into kilopascal, then it will be 5000 kilopascal. Further, pressure at the inlet is 1 bar. So it is also shown over here. Inlet is one number. So P1 is equal to 1 bar, 100 kilopascal. Further, temperature at the inlet is 27 degrees Celsius. So T1 is 27 degrees Celsius. And if you convert it into Kelvin, then it will be 300 Kelvin. Now you are supposed to find out efficiency and T2, T3 and T4. So let's start the numerical. Now let's assume that the value of V2 and V3 is 1 unit. So and value of V1 is 15 unit. So what will happen? The compression ratio is 15, right? So now first of all we will find out the value of gamma, that is adiabatic index, that is nothing but ratio of Cp and Cv. So Cp and Cv value is given, so gamma will be 1.4. Further, for process 1 to 2, that is reversible isentropic process, right? So you know that for that you can write down the temperature ratio as T2 is equal to T1 into V1 by V2 raised to gamma minus 1. So here you substitute the value of T1 and compression ratio, so you can get the value of T2, that is temperature at the end of isentropic compression process, that is 886.25 Kelvin. You can note down the value, so it will be helpful in further calculation. Now further, P2 is equal to P1 into V1 by V2 raised to gamma. Again this can be written for isentropic process. Remember, isentropic process is nothing but reversible adiabatic process. So for that you can write down the PVT relation, right? Pressure, volume and temperature correlation. So from that particular correlation, this P2 is equal to P1 into V1 by V2 raised to gamma is written. Here if you substitute the value of P1 as 1 bar, remember students, don't substitute the value of pressure in bar. Here whenever you are dealing with the numerical in thermodynamics, keep pressure in pascal or kilopascal. Okay, here V1 by V2 is 50, so substitute the value, then you will have the pressure P2 as 44.31 bar. Further, for process 2 to 3, what we can write is 2 to 3 is nothing but constant volume heat addition. So you know that if volume is constant, then pressure will be in proportion with temperature. So from that correlation, T3 is given as T2 into P3 by P2. Value of T2, P3 and P2 is given. So substitute the value, you will have the temperature 3 as 1000 Kelvin. Okay. Now T2 and T3 we have found out. The remaining temperature is T4. So for finding out T4, we will use the correlation for process 3 to 4. Now if you pay attention, then process 3 to 4 is nothing but constant pressure heat addition. So if you write down the equation of heat addition for constant pressure process, then Q is equal to mCp delta T, right? So from that particular equation, you can write down the value. Okay. Here the heat addition can be found out for constant volume process as QV is equal to CV delta T, right? So value of CV is given, T3 is given, T2 is given. So I can have the value of heat addition at constant volume as 81.71 kilojoule per kg. Further, for heat supplied at constant pressure is nothing but 1/2 of the heat supplied at constant volume. Sir, how have you written this particular correlation? How have you written taken the half value of heat supplied? So it is already given in the first line of the given data. Okay, so you can correlate or convert it into mathematical terms as this. Now further, substitute the value of heat supplied at constant volume. So you can have the heat supplied at constant pressure as 40.855 kilojoule per kg. Now further, write down the equation of heat supply at constant pressure. So you will have Cp delta T. So from this particular equation, you have the value of Q, you have the value of T3, you have the value of Cp, you can find out the value of T4. So T4 will be 1040.71 Kelvin. If you pay attention, students, then T4 is nothing but the highest working temperature of the dual cycle, and you can also appreciate that by observing the graph on the TS diagram. Okay, so T4 is the highest one and the value of the T4 is also the highest one. Now V4, that is the value of volume at the end of process 3 to 4. So V4 is nothing but V3 into T4 by T3. Sir, how have you written this equation? So it's very simple. Constant pressure process, that means volume is in proportion with the temperature. So that particular correlation is used over here. So you can find out the value of V4, that is equal to 1.0406 meter cube per kg. Now from process 4 to 5, that is nothing but reversible adiabatic expansion or isentropic expansion process, we can find out the temperature of 5. So that is equal to 357.93 Kelvin. Okay. Now thermal efficiency, you know that thermal efficiency is nothing but 1 minus heat rejected divided by heat supplied, right? So you can write down that equation, and from that equation the efficiency that we can find out is 0.6606 or 66.06%. So this is how you can deal with numerical of dual cycle. Today we are going to keep up to this point. Thank you.